Hi everyone and welcome to another lecture. So far we have seen these linear operators in a very abstract manner. Today we will want to look at some examples. So we'll start with the identity operator. You can denote it with I, and it is defined by the following action. Let's say you have this identity operator that is acting on a cat. It leaves it alone. That is its equivalent of doing nothing. And if you consider the finite dimensional case, this is just the identity matrix that has 1 in its principal diagonal and all the elements are 0 over here in both these places. So this is our identity operation. Then we want to declare an operator that will be very important in the study of physics, that is called Hermitian operators. So what is an Hermitian operator? Let's say you have some operator H and you dagger it and you get the same H. This is what is known as an Hermitian operator, and this Hermitian operator, they correspond to observables. So what do you mean by observable? So an observable is something that you can measure. That is, this Hermitian operator H will correspond to some quantity that you can measure. So an example would be position of a particle. It can be the momentum of the particle. It can be the energy of the particle, and so on. However, you can always have these things in the finite or infinite dimensional cases. For example, if you consider the position and momentum of a particle, you have to go to this infinite dimensional space. For energy, you can also do that, but when you are dealing with a spin half electron, that is, you can see that the energy operator, that is the operator that will give you the energy values and the states of the energy, will come in a matrix form. So let's try to look at that. For example, the Hamiltonian operator, Hamiltonian / the energy operator for an electron inside a magnetic field if you write it as H, it will be similar to, because the reason I'm writing similar again, because there might be numerical constants and stuff like that. So this will be the magnetic moment times the spin operator. So this is another operator, and this is also an observable. This is the spin operator. So let's call it the spin operator. And if you let's say you have this electron and it's spinning, it's not spinning, that's wrong to say, but it can have, let's say, plus half spin on the positive z-axis, and on the minus z-axis it can have this negative halves. So what Hermitian operator does, and this state, that is this up and down state, can be represented by a plus, that is 1 0 when it's on the positive z, and minus when it's on the negative z and it's 0 1. So you can think of it like this. And the operator correspond to this measuring these things is written as S of z, just to make sure that this is the z-axis that we're talking about, and it will be given by this h cut by 2, and you will have 1 0 0 minus 1. So when you are talking about this z-axis spin operator, this is a real operator. By real operator, it's not real operator, it's an Hermitian operator, because if you take S dagger, this is just h cut by 2 and 1 0 0 minus 1. So you can say that S bar of z, S dagger of z is equivalent to this. So this will be more clear when we deal with the eigenvalue problems. From there you can get the idea of the observable for sure. And in fact, if you want to have more examples of this Hermitian operator, another example would be the position operator. And this is represented by x. You can always give a hat if you want, but let's not give it for our course here. And this is an infinite dimensional operator. That is the vector space we're dealing with is infinite dimensional, and this is written as this. The way this is defined like this will be clear later, but let's move on with the discussion of the anti-Hermitian operator. An anti-Hermitian operator, let's say you have an operator omega. This is anti-Hermitian if you dagger it, that is if you take the adjoint of it, you pick up a minus sign and the omega itself. So this is an anti-Hermitian operator. And an example would be the derivative operator itself. So the reason for putting an I in this position operator over here is that this position is something observable, something real, and that's why to get the eigenvalues, though we haven't discussed eigenvalues yet, you will see that to get real eigenvalues that will correspond to a real number, that's why you have to put this minus I over here. So when you take the dagger of it, because of this anti-Hermitian property of the derivative operator, this thing will remain the same, and we'll discuss it more when we talk about the eigenvalue problem, and we'll discuss more about this Hermitian and anti-Hermitian operator when we deal with it. So let's just move on, and now we want to take a look at projection operators. Projection operators. So a projection operator is defined by the following. If this, okay, it looks a bit bad, so let's get rid of this. So this is a P, it's denoted by a bold, very bold P, and it's defined as, if you square it, that is, if you multiply it with itself, it will give you the same thing. That is, P square equals to P. This is the definition of a projection operator. If you can find a form, an operator that satisfies this condition, that's a projection operator. But the way we're going to deal with projection operator will also give us a very important identity. So let's try to do it. If you recall that we had our vector v written as like this, right? I, small vi, and the bases, right? And this vi were written as something like this. Oops. Right? Where this was just a number. That is, this part was just a number. And this, since this was a number or a scalar, and this is a ket, we can move it around, right? If you do it, something interesting will happen. Oops. And here if you write this v, that is this one you just write it here like the following, that is I over v, right? And if you pull this guy into this guy, that is you write the whole thing as I minus sum over I Now, how did I do it? That is, you might ask, hey, how did you go from this line to this line? The idea is to write I, V, and using the associativity axiom, that is, you saw in the last lecture, that if you had alpha, beta, and gamma like this, you could always leave this alpha over here and you could write it as beta and gamma. So that would correspond to some operator, and this is just a bra. So here we have used that associative axiom that Paul Dirac used to call the associative postulate for the brackets, or associative axiom of the multiplication. Here we have used that to our advantage, and we detached these I parts. And if you look at this equation, that is, let's call this equation 1, you can get a very nice identity that is known as this. So why is it so important? This is called the completeness relation. And you might ask, at this point we were discussing projection operator, so what are we doing with this thing, right? In fact, the very idea of this completeness relation comes from the projection operation. If you ask me how, okay, because there is a sum over this I over here. If you don't have a sum, that will actually correspond to a projection operator. Let me show you how this works. So we are calling projection operators as just I. That is, if you have I equals to 1, one of the projection operators could be just I equals to 1 like this. Let's say P1. And this is just this. So this is one of the projection. And if you add all the projections, then you should get the identity operation. The way to see it can also be drawn from the vector analysis, but let me do it in this bracket framework, because if you see that this guy, that is, if you expand this guy, this is just what? V1 1, V2 2, V3 3, dot dot dot, Vn n, right? And the way to get a component, okay, let me just go down below and write this whole thing again. Okay, so let me just write it quickly. V2 2, Vn n, right? And let's say you want to know the one component or the second component or the third component. So how do you do that? You just, let's say I want to know the third component, so this is what I do, right? And this gives me V3, and this 1 2 3, these were my basis vectors. So this inner product is like a projection. If you compare this with the vector analysis thing that you learned, that is the Euclidean 3D space, if you take a projection first, you can make a projection along the z-axis, right? Let me just use another color. Let's call it green. And this projection that is marked with green, oh my god, this would give you the z component, right? And the way to do that was, if this was a vector called A, let's say the arrow, you had to dot product with the unit vector, and so on. You could also get the x component by using, let me just write it down, just dotting it with the x hat vector, that is the unit vector on the x-axis. So a similar thing is happening here. That is, whenever you are taking inner product, you are taking some projection, and the operators that we write like this, this will help you to do that. So what I want to do, instead of dotting, I want to have an operator and I want to act it on a vector, and I expect that operator to give me the component on the basis that I'm using inside the projection operator. So let's see how we can work this out. So again, let's remember that P was I, something like this, right? And I have an expansion of V that is going like this. Let's say J. I'm using another dummy variable. It doesn't matter, but it's a good practice to do it in a general manner. Now, okay, what I want to see is that what is P acted on V. This is the thing I want to see. And if I accept this definition, then you just plug it. Again, using the associativity of the operators that we talked about earlier, that is the bracket sandwiching. This is just this, right? And what do you have here? So far nothing, because we haven't written down this sum yet. So even if you don't write it explicitly, you can always say this is Vi, right? So this is how you can get the component with the basis intact. So this is how projection operations work. And if you want to know the proof that projection squared is equals to projection itself, this is also easy, because if you write a projection operation as, let's say, this P square is written as Pi and Pj, and we want to see what is the resulting output. So Pi will be denoted by this and Pj will be denoted by this. And since these are basis vectors, orthonormal basis vectors, and you can use the bracket sandwiching, but here you have to be a bit careful. First you want to sandwich these two guys that is in between, that is I and J. Now this is an inner product, so that's a number. You can move it around, and this number is nothing but delta ij, right? So this is I, delta ij, and j. But the only non-zero contribution will come when this I and j are equal. So the only non-zero contribution will happen when there is no difference between I and j. So this will be just, let's say I want to keep the I and I want to replace j with I, so this will be just this QED. And the final thing that we're going to look today is the completeness relation that we mentioned a bit earlier. This will be very important when you when you manipulate the bracket, manipulating the bracket notation, the completeness relation. And I'm going to we already proved it in an abstract manner, but I'm going to show you in a explicit manner how you can work this out. Let's start, and we are going to take column vectors I. Let's say, okay, not I. We're going to consider a very simple system. So let's say 1 is equals to 1 0 and 2 equals to 0 1. So what we are considering? We are considering a vector space that has two elements, and that is two bases. That is, it's a dimension 2 basis, and we are going to see what is this summation gives us. That is I, and it will start from 1 and it will run up to the dimension of the vector space. For here it will be 2, so this will be 1 1, right? And you will have 2 2. Very simple thing to do. And recall that we, in our past lectures, we saw how to evaluate outer product, but here I'm going to show you explicitly again. So 1 was 1 0, that is the ket of 1, and the bra of 1 was 1 0. Similarly this is 0 1 and this is 0 1. And to do an outer product, what do? We keep this 1 and we multiply this whole row thing with this each of the elements, right? So this is how we write, and the resulting thing should be a matrix. So 0 1 0 and 0 times 0 1, this is 1 0 1. So oops, sorry, there is something over here. So then what we do, we just multiply. So this is 1 0 0 0 and this is 0 0 0 1, and if you add them, what do you get? You get the 2 cross 2 identity matrix. And similarly, you can go for n dimensions, where each of these columns, that is i's, let's say it's the instead of I, okay, just take the n, just so that you can understand what I'm saying. It's that, let's say you have an entry m in an n-dimensional space, that is n-dimensional vector space. So all the elements above m will be 0, the mth entry will be 1, and all the way down to n will be also 0. So this is a basis, and you already know how to write bases for n-dimensional vector space where n is a finite number, and this will be the completeness relation. In fact, this completeness relation will also have another form, that is, instead of these discrete sums, it will have an integral associated with it when we talk about infinite dimensions. So I don't want to talk about that right now, and this will be it for today.